Welcome to Power Electronics Education, Electronic Book, Lecture 7, Isolated DC-DC Converters. This lecture is presented by Dr. FIRUZ ZARE. So why we need isolated DC-DC converters? Basically, in some applications, we need to have galvanic isolation because of protection and safety. So in this case, we can use transformer. So the advantage of transformer is that we can have multi-outputs, and also at the same time we can have galvanic isolation. But basically, using switch mode power supply or DC-DC converters which operate at high frequency, if we use transformer which operates at high frequency, then we can decrease the size of transformer. A simple power supply which has galvanic isolation is based on a transformer operating at line frequency. That means we can have a step-down transformer, and this transformer is connected to the grid, 220 volts at 50 Hertz. But the point is that this transformer is connected to a diode rectifier, and we can get DC voltage using this capacitor as a filter. So basically, this is a simple method in which we can regulate the output voltage, but in some applications, because here we have no control on the output voltage, because diode rectifier just rectify the voltage, and also transformer just change the voltage and also at the same time makes isolation. So in this case, we need to have another DC-DC converter here to be able to control the output voltage and regulate it. While here, when we have transformer operating at high frequency, the advantage is the size of this transformer is smaller than this transformer, because this one operates at line frequency 50 or 60 Hertz, while this one can operate at higher frequency, for example few kilohertz. So the point is that the input voltage is much larger than here. So in this case, we may have 200 or 300 volts DC voltage, and in this case we change the output voltage based on the conversion ratio and based on the topology. A flyback converter operates similar to buck-boost converter. Even the conversion ratio is almost same as the one in buck-boost converter. So the advantage of flyback converter is simple and cheap, and also suitable for low power applications. In some power electronic systems, we need to have power supply for control circuit, for gate drives with galvanic isolation. So flyback converter with multi-output is a good candidate for these applications. So basically, it can operate at low power, less than 100 watts. But forward converter basically is similar to buck converter, except here we have galvanic isolation, and also we can have higher power compared to flyback converter. So that means the output power can be few hundred watts, and in this case the size of transformer is smaller than the one in flyback, and the reason is that we do not store energy in the core itself. That means compared to flyback, the size of transformer is smaller, because in this case we just transfer the power from primary to the secondary side, while in flyback we charge the transformer and then pump it to the output. So this is a circuit diagram of a flyback converter. Here we have a transformer with this conversion ratio, a diode, and also capacitor, and this is load resistor. So we have a switch here. In this case, we can model a transformer as an ideal transformer in parallel with an inductor, which is basically magnetizing inductor, and we can consider same analysis that we have described in DC-DC converters. So let's look at the case when the switch is on. So when the switch is on, the input voltage appears across the primary side, with this polarity, because the input voltage is positive, in this case diode is off. So that's why in this case the second part consists of this capacitor and load resistor. That means capacitor is discharged through this load, and in this case we just charge the magnetizing inductance. So when the switch is off, then the energy stored in this inductor, or the energy stored in the transformer, is transferred to the secondary side. So in this case, if we look at the current source, because the current before switching off through the inductor was in this direction, so now in the secondary side, that is the direction of current in the secondary side. And here if you look at the diode basically conducts in this case. So in this case we have output voltage appears at the secondary side and basically appears at the primary side. So now we can write the equation for flyback converter. Basically when the switch is on, the input voltage equals to input voltage appears across the primary side, which is basically across the magnetizing inductor. So this is the equation, and in this case the capacitor is discharged through this load resistor. So this is the equation. Suppose that the ripple is not significant, then we can rewrite the equation as described here. So when the switch is off, basically the inductor, the current through the inductor is circulated through the primary side, and basically we have current at the secondary side. So now here we can write the equation. So the voltage across the secondary side equals to minus V out, which is given here, and because of this turn ratio we can find the primary voltage in terms of secondary voltage, and if we put the secondary voltage in this equation, we have primary voltage in terms of output voltage and turn ratio of the transformer. So the voltage across the inductor basically equals to this equation. And also we can write the current through the capacitor, and in this case this is the current through the capacitor, which is equal to I2 minus I load. So this is load current V out over R, and this is I2 current through the secondary. So in this case, suppose that the ripple is not significant, we can rewrite the equations, and we have voltage across the inductor when the switch is off, and we have current through the capacitor when the switch is off. So as we mentioned before, in a steady state the average current over one switching cycle should be 0, otherwise the system is not in a steady state. So in this case this integral should be equal to 0. So we have the current through the capacitor when the switch is on and when the switch is off. So we need to find this value, which is basically this term associated with the time that the switch is on, and this term when the switch is off. So when we simplify this equation, finally we can find that the current through the inductor equals to this ratio, in this case assuming that the ripple is not significant. And also we can find the output voltage. That means in a steady state the average voltage across this inductor or magnetizing inductance should be 0, or this integral should be 0. When the switch is on, we have this DC voltage, and when the switch is off, we have this voltage across the inductor. So this is for when the switch is on and when the switch is off. So the average means that this area. So here we can find the conversion ratio and conversion ratio V out over V in equals to d over d prime times of n2 over n1. So basically here shows that this is equal to buck-boost converter considering the conversion ratio of the transformer. We can also find the ripple. Ripple means that ripple of the magnetizing current. So when the switch is on, input voltage appears across the primary, which is basically across the inductor, and this voltage equals to Lm di dt. So for this period, because we can define delta Im as this magnitude, so from this point to that point we have this current change, which is basically 2 delta Im over delta t, which is basically delta t is dts. Then we can find the ripple in terms of input voltage, magnetizing inductance. So basically till now we haven't considered the leakage inductance. Let's see what happens when the switch is on and off. So when the switch is on, we have current through this leakage inductance and magnetizing inductance, which is basically given here. This is for the time that the switch is on. And when the switch is off, basically still we have current before turning off the switch. We have current through this inductor, and also we have current through this inductor. When we switch it off, this current is circulated through this circuit, through primary, but there is no loop for this current. That means here we have, we force this current to 0. In this case we have the IDT times of this leakage inductance gives the over voltage, and this over voltage may damage the switch because it's appear across the switch. So in this case we may need a snubber circuit to be able to control the voltage across the switch. So this is a circuit diagram of a forward converter. Basically here we have a transformer which operates at high frequency, and here we can see that this part of circuit is similar to buck converter. Basically, as I mentioned before, forward converter is similar to buck converter with galvanic isolation. So when the switch is on, here we can see that the input voltage appears across the transformer primary side, and because of this polarity we have same voltage here, and because the input voltage is positive, so that's why this diode which placed here conducts. So in this case we have current through the inductor similar to a buck converter. But when the switch is off, then here, because if you look at the circuit diagram, the current through the primary side cannot go to the secondary side, because basically here we can see that there is a diode. Because this is the direction of current, so basically in the secondary we should have this direction of current, so that's why this diode is off, cannot conduct. But here we can see that basically this inductor, here we can see that the current through the inductor passed through this diode. So now we can find the current through the magnetizing inductance when the switch is on. So in this case the voltage across the primary is equal to input voltage, because when the switch is on the input voltage appears across the primary. So this is the equation, and because of this turn ratio, so the voltage across the secondary is given by this equation. But the point is that the input voltage equals to voltage across the magnetizing inductance, and in this case we can find the current through this magnetizing inductance. So basically at the end of this cycle, when the switch is getting off, this is the current through the magnetizing inductance, and when we look at the time when the switch is getting off, Because the current through the magnetizing inductance is basically at this level, so basically this current through the primary should be flown in this direction, but because of diode there is no any current loop. That means the current is forced to zero. Basically we have significant dIdt times of magnetizing inductance. So we have large voltage spike over voltage which may damage the switch. So in this case this circuit diagram doesn't work for forward converter, and the solution is basically using an extra winding which may provide a current loop for the time when the switch is getting off. So let's start with the case that the switch is getting on. So similar to previous circuit diagram, the input voltage appears across the primary, and then we have positive voltage across the secondary. So this circuit is almost similar to buck converter. And now let's look at the case when the switch is getting off. So when the switch is getting off, so this switch is off, and in this case because we have current through the magnetizing inductance, so if this is the direction of current, that means the direction of current in this winding should be in this direction. And if you look at the diode here, so this circuit diagram shows that the current can be flown in this direction. Now we can see that in this section this voltage define the voltage across the primary, and also here because of current through the inductor this diode conducts, and basically we have this circuit which is basically similar to buck converter, and we have this circuit which defines the energy stored in the magnetizing inductance is getting back to the power supply. So now we can write the equation. So suppose that the voltage drop across the diode is not significant, is almost zero. So in this case we can see that this input voltage appears across this now we can see that the input voltage appears across this winding, and in this case V3 equals to minus V in, and because of turn ratio here, so the voltage across the primary is given by this equation. That means we have negative voltage which force the current to be decreased, and this is the voltage across the magnetizing inductance which is minus V in times of N1 over N3. And in this case we can find the average voltage across the inductor. So let's find the average voltage over one cycle. Basically in a steady state the average voltage should be zero. If you look at the voltage waveform, basically when the switch is on, the voltage across the primary or magnetizing inductance is V in. So we can basically find this area and this area, and the average should be zero. So this is basically the average voltage when the switch is on, and when the switch is off, this is the voltage across the magnetizing inductance times of this duty cycle and this time. We can simplify the equation. That means this duty cycle depends on duty cycle times of this ratio, 10 ratio. And we know that this is the maximum d prime, and in this case d2 should be less than d prime. So when we simplify and put the value in this equation, we can simplify the equation, and finally we can see that in forward converter the maximum duty cycle is given by this equation. So that's why if N3 divided by N1 is equal to 1, so the maximum duty cycle that the forward converter can handle is less than 50%. So this is one of the problems that we have to understand. Now we can concentrate on this part of circuit which is basically equal to a buck converter. So here we define a voltage, which is basically Vk, and when the switch is on and off, we have this voltage waveform across the diode. That means when the switch is on, the input voltage appears across the primary. With turn ratio, we have the voltage across the secondary, which is basically this voltage. And when the switch is getting off, because this diode doesn't conduct, so because inductor current can bias the diode and diode conducts, so the voltage across the diode is 0. So that means this circuit, which is basically buck converter, has this voltage waveform, and based on this turn ratio, we can see that forward converter is basically like a buck converter with galvanic isolation.